Today let's look at section 12.1, exponential functions. A function that can be written in the form f of x equals b to the x, where b is greater than 0 and b is not equal to 1, is called an exponential function with base b. The reason we don't want b equal to 1 is that would be a constant function. 1 raised to any power is going to be equal to 1. So that's why we exclude 1 from our base. Here are some examples of exponential functions. The first one is f of x equals 2 raised to the x. The base is 2, and notice how the exponent x is the power. F of x equals 10 raised to the x is also another example of an exponential function. The base can also be a fraction, such as 1/3, and sometimes we have an exponent that is negative. This is 4 raised to the negative x. Let's look at example 1 now. Let f of x be equal to 3 raised to the x. Find the following: f of 3. That means we'll take the base, which is 3, and raise that to a power of 3. This simplifies as 3 cubed, which I know is 27. To find f of 0, you'll take the base 3 and we'll substitute that x as a 0. 3 raised to the 0 power, that is equal to 1. You can check that with a calculator, but you can also remember that anything raised to the 0 power is equal to 1 except 0. So x to the 0 is equal to 1 for all values of x except x being 0. In part C, again we'll do the same process. We're raising this to an exponent of -2. So let's write this as 3 to the -2. But recall, x to the negative n is equivalent to 1 over x to the positive n. So I could rewrite this as a fraction, 1 over 3 squared, and this simplifies as 1 over 9. In example 2, let f of x be equal to 4 raised to the x. Let's find the following. Part A, f of 5. We are going to substitute a 5 for the x, and so this is 4 raised to the 5th power. We can use our calculator now. 4 raised to the 5th power is equal to 1024. In part B, we'll substitute a -3 this time. 4 raised to the -3 is equivalent to 1 over 4 to the positive 3. Again, if we have a negative exponent, we can send that to the denominator as 1 over x to the positive n. So this again is a useful formula to remember. 4 cubed, I can simplify that. 4 cubed is 64. Our final answer is 1 over 64. In part C, we have f of 8. We'll take the 4, raise it to the 8th power, and we'll simplify this with a calculator. 4 raised to the 8th power is 65,536. Double check with your individual calculator, making sure you know how to use your own calculator. Again, 4 to the 8th is 65,536. Double check with your personal calculator. Example 3, let f of x be equal to 5 times 3 raised to the x minus 4 plus 16. Let's find f of 6. The first step is to write f of 6, and then we could do the substitution. We'll substitute the x with a 6. This is 3 raised to the 6 minus 4 plus 16. We have to do the exponents first, so we'll do the 6 minus 4 first. This is 5 times 3 raised to the 2nd power plus 16. The power has to be done next now. we have to do 3 squared, and that gives me a 9. So this is 5 times 9 plus 16. And then we'll do the multiplication. 5 times 9 is 45. And then we'll have to add 16. 45 plus 16, that's going to give us 61. When you write your solution, we only need to write f of 6 once, and we make sure our equal signs are always lined up until we reach the end. In example 4, it's a similar process. We'll write f of -1 first, then we can plug in the -1 into the x. This is 2 times 7 raised to the -1 plus 3 minus 19. We'll do the exponent here first. -1 plus 3, that's going to give me a 2. This is 2 times 7 squared minus 19. 7 squared is our exponent. We'll have to do that. 7 squared is 49. This is 2 times 49 minus 19. We'll multiply next. 2 times 49, that's going to give me 98 minus 19. Finally, we'll do the subtraction. 98 minus 19. That gives me a 79. Let's look at example 5. A similar process. We always start by writing f of 2. That's what we're substituting into the x. So we have f of 2 equals 3 times 5 squared plus the 4 plus 50. Again, I'll focus on that 2 plus 4 first because that's inside the exponent. This is 3 times 5 raised to the 6th power plus 50. Now we'll have to do the exponent, the 5 raised to the 6th power. 5 raised to the 6th power is 15,625. We'll multiply next. That's the orders of operation. After multiplying, we have 46,875 plus that 50. And we can simplify that now as 46,925. That's our final solution. In example 6, let's graph f of x equals 2 raised to the x and also state the domain and range of this function. I'll start by making a table. On the left, we'll pick some x values. Let's pick -2, -1, 0, 1, 2. This is so we can see the general shape of 2 raised to the x. We'll start with the easy one first. 2 raised to the 0 power, that's equal to 1. 2 raised to the 1 is equal to 2. 2 squared is going to be 4. Now, what's 2 raised to the -1? We could do the scratch work here on the side. That's equal to 1 over 2, or 0.5. So I'll just write 1/2. And 2 to the -2, you can simplify that as 1 over 2 to the +2, which is equivalent to 1/4. So we can plot this point on the graph. I'll start with -2, 1/4. And we're just doing a sketch here, so we don't have to be perfect. -1, 1/2. 0, 1, 1, 2, and 2, 4. So this is our exponential function. It looks like a smooth curve, and it goes up forever. It does go up forever, but it never, ever touches the x-axis. We have a horizontal line here that it never touches. It'll get closer and closer to it, but it will never reach this line. You can see the pattern: 1/4, 1/8 would be next, 1/16, and so on. So it gets closer and closer to this horizontal line, which we're going to call an asymptote. This is an asymptote because it approaches it forever, but it will never, ever reach that line. Now, what is our domain? Our domain is how far left it goes to how far right it goes. So it goes to the left forever, it goes to the right forever. That's not too difficult to find. But the range is different. The range, it doesn't go to 0. It can get as close as we want to 0, but it will never reach 0. So we'll use a parentheses. Do not use a square bracket. It cannot reach 0, but it can get as close as we want. So use a parentheses, but it does go up forever. So the range is a parentheses 0, comma, infinity. A asymptote is a horizontal line that the graph of a function approaches as it moves to the right or left. An increasing function is of the form f of x equals b, where b is greater than 1. This is a typo. It's greater than 1 and not 0. So let's fix that on our notes. Again, an increasing function is of the form f of x equals b raised to the x, where b is greater than 1. When we have a base that's greater than 1, our function grows as we go to the right. As we go to the right, our exponential function is increasing if the base is greater than 1. Example 7. We have f of x equals 3 raised to the x, and also state the domain and range of f of x. Notice our base is a 3, that's greater than 1, so we know this is going to be an increasing function. I'll start by creating a table of values, let's say -2, -1, 0, 1, 2, and on the right we'll look at 3 raised to the x. 3 raised to the -2, we'll do the scratch work here, is equivalent to 1 over 3 squared, or 1 over 9. 3 raised to the -1 is equivalent to 1 over 3. So we'll write 1/3 here. 3 to the 0, well, that's going to be equal to 1, because anything raised to the 0 power is equal to 1, except 0. 3 to the first, that's easy to do, that's just 3. And 3 squared gives me 9. So let's graph the values. -2, 1/9. It's really close to the x-axis. -1, 1/3. Just a little bit higher than the previous one. 0, 1. That's our y-intercept. 1, 3. And then we have 2, 9. So it looks like the previous graph, except it's growing a lot faster than the example 6. In example 6, it was growing, but it wasn't as fast as this. And why is that? Well, the base is larger. The base is 3, so it grows a lot faster than a base of 2. And again, we're going to draw this horizontal asymptote with a dashed line, because it's not part of the graph. This is our asymptote. We'll state our domain. It goes forever to the left, and it goes forever to the right. Even though it's pointing straight up, it actually has a little bit of an angle to it. So the domain is -infinity to infinity. The range is the same as the previous example. It just goes down to 0, but it's a parentheses, not a bracket. This is 0, infinity. In example 10, the base is even bigger. So let's compare example 7 and 8 together, and let's see what's going to happen. I'll pick some values here. Let's pick x as -2, -1, 0, 1, and 2. And for the other side, we'll look at 10 raised to the x. So this is 10 raised to the -2, which is equivalent to 1 over 10 squared, or 1 over 100. That's really close to the x-axis. 10 raised to the -1 is equivalent to 1/10. 10 raised to the 0, that's equal to 1. And 10 to the first, we all know that's 10. 10 squared that is equivalent to 100. That's going to be off the charts. So we'll plot negative 2 comma 1 over 100. That's really close. And negative 1 comma 1/10 is really close also, but a little bit higher than the previous one. 0 comma 1. 1 comma 10 is way up here, and we can't even plot 2 comma 100. It's just so high up there. So we'll draw our graph. It has a really steep slope, but it does continue to the right. And don't forget your horizontal asymptote here on the x-axis. Now we'll state our domain. The domain and range is the same as the previous example. The domain is negative infinity, comma infinity. And for the range, it does go down to a 0, but never touches it, so use a parentheses. This is 0, comma infinity, and that is our range. In example 9, you have a base here that is less than 1. So this is called a decreasing exponential function. It's going to get smaller as we go to the right. I will start by picking values of x and then substituting it into my function. Let's pick negative 2, negative 1, 0, 1, and 2. 1/3 raised to the negative 2 is equivalent to 1 raised to the negative 2 divided by 3 raised to the negative 2, which, if you deal with the negative exponents and swap their locations, this is equivalent to 3 squared over 1 squared, which is equivalent to 9. So this gives me 9. 1/3 raised to the negative 1 is equivalent to 1 to the negative 1 over 3 to the negative 1. And again, if you deal with the negative exponents, this is equivalent to 3. 1/3 to the 0, that's always going to give us a 1. 1/3 to the 1, that is just 1/3. And 1/3 squared is 1 squared over 3 squared, which is 1/9. Let's plot negative 2 comma 9 first. Negative 1 comma 3. 0 comma 1. 1 comma a third. And 2 comma a ninth. And you can see it actually looks like an exponential function, but it's decreasing really rapidly this time. It does not touch the x-axis again. This is another asymptote. The domain is still to the left forever and to the right forever. The domain is negative infinity, comma, positive infinity. For the range, it goes down just to the x-axis, but never touches it. So the 0 with a parentheses, comma, infinity. In example 10, we have, again, the base is a 1/2. That's less than a 1. So this is a decreasing function. We'll start by making our table again and plugging in the values. I want you to try this on your own, and after you complete it, compare with my answers. So let's do negative 2, negative 1, 0, 1, and 2. So give it a try. Let's fill in the right side for me. And so you should get 1/2 raised to the negative 2 is equivalent to a positive 4. 1/2 raised to the negative 1 is equal to 2. 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. And 1/2 squared is 1/4. Let's plot the values. Negative 2 comma 4. Negative 1 comma 2. 0 comma 1. 1 comma a half, and then we have 1 or 2 comma 1/4. So this is still a decreasing function. And we do have another horizontal asymptote. And so our domain, if you look at the graph, is the same as the previous examples. It's not always the same. Look at the picture, then decide. It goes left forever, right forever, goes down just to 0 but doesn't touch it, and it goes up forever. Sometimes we have a exponential function with a natural base. The natural base is denoted with the letter E. This is a constant term, and it appears a lot in mathematics, just like the number pi does in nature. Pi appears in relationship to a circle. E is something very similar to pi. It is an irrational number that repeats forever. And here is an approximation of E. E is approximately 2.71828, and so on. It does go on forever. It does not repeat, and it does not terminate. The natural exponential function, will define that as f of x equals e to the x. This is on every single scientific calculator. So locate that button on your scientific calculator. It's usually located next to the ln button. So look for that ln button or natural log button, and you'll find e next to it. So let's try f of 5 for the natural exponential function. And so in part A, we're looking for e raised to the 5th. I want you to practice with your calculator e raised to the 5th. And e to the 5th, you should get 148.413. Again, double check with your own calculator so you know how to use it for e. In part B, we're looking for e raised to the negative 1.7. Again, type that in that calculator. And my calculator says it's 0.183. Part C, I don't need a calculator. I know e raised to the 0, that's always going to be a 1. So practice on example 2 now. Use your calculator and making sure that you get the same answer as I do. In part A, this is a substitution problem. We'll plug in a 1. So this is e raised to the 1 minus 2 plus 7. And that's equal to, we'll do the exponents first, e to the negative 1 plus 7. Enter that in there. I would recommend you put parentheses around the negative 1, so it does the first part first, and then it adds the 7. And this simplifies to 7.368. For part B, we'll look for e raised to the 5 minus 3 plus 7. This is equivalent to e raised to the second power plus 7. And again, we'll simplify this, making sure we have a parentheses around that 2 for our calculator. And this gives me an answer of approximately 14.389. In example 3, we will depend more on our calculator, so we'll enter these values in. Let's do negative 2, negative 1, 0, 1, and 2. I'll use my calculator to evaluate e to the negative 2, e to the negative 1, e to the 0, e to the 1, and e squared. Again, we'll approximate all of these values. E raised to the negative 2 is equivalent or approximately 0.135. E to the negative 1 gives me approximately 0.368. E to the 0, we know that's exactly 1. E to the 1 is approximately E to the 1 is approximately 2.718, and E squared is approximately 7.389. Now notice that base E is greater than 1, so I expect this to be an increasing function. We have negative 2,0.13, and we're just going to estimate where that is. 0.3 is a little bit higher, 0.368 is a little bit higher. E to the 0 is 1, so this is exactly 0, 1. We have 1, 2.7, so that's pretty close to 3, but not quite 3. And then E squared is 7.38, so we'll just say that's pretty close to 7.5. We're just sketching our graph here. We don't have to be precise. And we do get an exponentially increasing function with the same horizontal asymptote. And I want you to figure out what the domain and range is. And that should give you negative infinity, infinity. And the range is down to 0 and up forever. So the range is 0, infinity. In example 4, we want to use a property where if the base of a number raised to a power is equal to another base raised to a power, and the bases are the same, then we can say that the exponents are the same. So if you have a base raised to an exponent and the same base raised to an exponent, and they're equal, well, the only way that they could be equal if they have the same base is the exponents have to be equal. So that's what this property is saying. Again, if the bases are the same and they're equal to each other, well, the exponents better be the same. That's what we're going to use for example 4. I want to solve for x. So let's solve for x by rewriting the second part. I will try to get the same base. 2 to what power will give me 16? Well, that's a 4. Since the bases are the same, well, that means the exponents better be equal because this is equal. So we'll say x equals 4. This is our first solution. In example 5, we'll try the same strategy. 4 raised to the x is equal to 4 raised to what power? Well, I want to get 256. And if you check with a calculator by trial and error, you can say 4 squared, that's 16, that's too small. 4 cubed, that's 64, that's still too small. What's 4 to the 4th? 4 to the 4th gives me 256, and so I can rewrite this as 4 to the x equals 4 raised to the 4, because I know 4 cubed, or actually 4 to the 4th, is 256. And what does that tell you? Well, since the bases are the same, it must mean the exponents are equal. So x equals 4 as well for this example. In example 6, the idea is to get the same base. We have a fraction here, so that implies my base must be negative. So 5 to the negative 1, that's 1/5, that's not right, so we'll try 5 to the negative 2, that's 1 over 5 squared, which is 1 over 25, and that's not right either, so we're getting closer. 5 to the negative 3 is 1 over 5 cubed, which is 1 over 25, or 125, and so that's the correct exponent. The negative 3 is our correct exponent, and so I can write 5 raised to the x is the same as 5 raised to the negative 3. But since the bases are the same, what can we say about the exponents? Well, the exponents are also the same, so x must be equal to negative 3. In example 7, I want to get the bases the same, so let's choose a base of 3. 3 to what power is going to give us a fraction of 1 over 27. And if you check through trial and error, you will realize 3 to the negative 3 is 1 over 27. And so I'm going to use an exponent of negative 3 here. Since the bases are the same, well, we can say that x plus 2 must be equal to negative 3. So that's what we're going to solve. X plus 2 equals negative 3. Subtract that 2 to both sides. X must be equal to negative 5. This is our solution. And if I'm not certain about that, we can always plug it back into the original, and you will see that it does work. In example 8, what do you think our base is going to be? Well, this is a big clue. That's 7. 7 raised to the 5x minus 17 is equal to 7 to the something is going to give me 343. And you could use your calculator to double check. I know 7 squared is too small, so I'll check 7 cubed. 7 times 7 times 7 3 times does give me 343. So I know 7 cubed is 343. So we could replace this on the right with 7 cubed. That's what we want. Since the bases are the same and they're equal, well, that means this exponent has to be the same. So we can say 5x minus 17 is equal to 3. We'll add that 17 to both sides. 5x must be equal to 20. And if you divide both sides by 5, x is equal to 4. That's our solution for example 8. In example 9, always try to get the bases the same. Well, we already have that situation. So the exponent must be the same. This has an exponent of 2x plus 13. And we're going to set that equal to, well, what is this right here? What's the exponent? It's an invisible 1. So we'll set this equal to 1, not a 0. This is a 1, not a 0, because 9 to the 0 would be equal to 1. 9 to the 1 gives me 9. So there's an invisible exponent of 1. And we could solve for x. Let's subtract 13 to both sides. 2x equals negative 12. And divide both sides by 2, we have x equals negative 6. Again, if I'm not sure this is right or not, we can always substitute that negative 6 into the original equation, making sure we get a true statement. And if I'm double checking this, I will get 9 to the first is equal to 9, and that's true. So you can always check your problems for these examples. In example 10, we have 3 raised to the 4x plus 3 equals 1 over 243. I know I have to have a negative exponent, and so if you check 3 raised to the negative 5 is going to give us 1 over 243. And that's by guessing and checking with a calculator. So I'll substitute here a negative 5. So 3 to the negative 5th is exactly 1 over 243. Since the bases are the same, we can equate the exponents now. 4x plus 3 equals negative 5. I can add or subtract, and we'll subtract 3 to both sides. 4x is equal to negative 8. And that means if we divide both sides by 4, x is equal to negative 2. In example 11, this one looks like an interesting problem, but it's not too difficult if we get the bases the same. So I could rewrite 16 as 2 raised to the fourth power. 2 raised to the fourth power is equivalent to 16. Since the bases are the same, we can equate the exponents. So we'll say x squared plus 3x minus 6 is equal to 4. We know how to solve these. These are quadratic, so let's subtract 4 to both sides, set it equal to 0, and hopefully we can factor this thing. And this does factor as x plus 5 times the quantity x minus 2 is equal to 0. So we're reviewing factoring. And this means x is equal to -5 or x is equal to +2. So we actually have two solutions to this problem. Example 12, I want the bases to be the same, so let's rewrite the right side with a base of 3, and the exponent here is a 3. 3 cubed is going to give me 27. Since the bases are the same, the exponents has to be the same because they're equal. So we'll say x squared minus 8x plus 15 is equal to 3. And again, we could subtract 3 to both sides and get something here equal to 0. And it factors. This factors as x minus 2 times x minus 6 is equal to 0. Which means we have two solutions, x equals a +2 or x equals a +6. Again, review factoring if you're not sure how to do that. We use factoring for this problem. We could also use the quadratic formula, but factoring is a lot faster. Example 13, we have a word problem. The population of a particular small town can be approximated with this function. F of x equals 75,000 times e raised to the 0.018x, where x represents the number of years after 1990. What will the population be in 2020? Well, to do this, we'll have to figure out how many years there are. Well, if I take 2020, subtract 1990 from it, I get a span of 30 years. So this is the time it takes from 1990 to go to 2020. To solve this problem, we'll need to find f of 30. We're going to substitute a 30 into our equation. We have 75,000 times e raised to the 0.018 times 30, and we'll simplify this. And since we're talking about a population, let's round to the nearest whole number. And here's my solution, 128,701. So this is how many people will be in that town, 128,701. If you didn't get that answer, you probably forgot a parentheses before the 0.018 and after the 30. That's the most common error that I see. So double check that you can get that answer with that calculator. Example 14. Wendy deposited $5,000 in an account that pays an incredible 13% annual interest, compounded annually. The balance after t years is given by the function f of t equals 5,000 times 1.13 raised to the t. What will the balance be after 40 years? For this question, we'll look at f of 40. We'll substitute that 40 into the equation for the t, which is the time. And we'll simplify this to the nearest cent because we're talking about money. So let's simplify it to 2 decimal places. And this is going to give us 663,907.76. So this is a lot of money. This is $663,907.76 for this. It took us 40 years, but we were able to get more than $500,000. That is pretty good.